Very good evening, Nishant. Can you guys hear me? I think only three people has joined: Suraj, Nishant, and me. Can you guys hear me? Thank you for confirming. How you guys are doing? All good? Great, great, great. I'm hoping you guys have practiced it. Whatever we have learned, or I believe you guys have also a test right on Sunday. How was your test? Yes, AWS. Is it any short form or you are talking about? Oh, awesome. Hmm. Nice, nice. So test was good, right? What type of problem like you guys got there? Like I remember the pattern you guys were sharing. The problem like the pattern was the second round would be two questions would be there, right? Some problem solving question would be there. What was those two questions? Create models. That is from the previous class, right? We were talking about the database models and those things. What what was there here from data structure or these problems? Any problem you got from data structures? Very good evening, Arad. I was just asking about the test, guys. Oh, so no, like the test is still happening on the previous module, specifically on Node.js side. Good, good. Okay, you were sick. What happened, Arad? Watch the older recording, Suraj. It's not difficult. It's very easy. Each models have some attributes, and those attributes you need to like when you have multiple models, you need to create relation between them. Yeah, fever and cold. Yeah, it's happening actually. It's happening. As you know that it was happened to me as well. Still, I feel little bit cold, but yeah, I'm fine right now. So please take care, everyone, because weather is changing here. So yeah, please take care. Again, I'm saying, I think whoever is staying on north side of India, so because weather is changing here, if you talk about the like Calcutta, Hyderabad, and little bit more down, so temperature is I think normal there. But I think on the North India, temperature just goes down here. So that's why please take care, everyone. Very good evening, Joseph. Nishant is saying, so what is the mostly asked DSA topics in interview? So there are a lot of questions happen with the arrays actually. Lot of things happen with arrays only. Every time like bigger organizations, they start very small questions and then like you have to give the answer first to that question and then they are looking for optimization like Google or Facebook or this type of organization they look for first you solve the problem in brute force approach like with maximum time complexity then they want you to solve it with the minimum time complexity. So now this is the thing which they are going to ask you everywhere, right? So now for for doing all these things like optimizations you have to know a lot of things like which data structure can provide you more optimizations or which sorting algorithm can provide you more optimizations or which like queues or stack could provide you how to use that queues and stack. So that's what actually it happens. So in interview they simply ask you questions but while solving these questions you can use like any topics from the DSA. There is no any specific topic which they will be looking for. But yes, if we talk about the trees and graph, so a lot of problems I have seen that they ask around this topic, trees and graph. So definitely graphs are more important. In some organization I've seen that uh, they will give you like one question on graph, finding out shortest path and all those things. First they ask for brute force approach. They do not ask for, they just ask you to give them the solution. So it looks like you start with brute force approach for any new question, like how to solve it first with any approach. Then you start optimizing the solution. Okay, Joseph? So we'll wait for 1 more minute and then we'll start our interesting topic 3. Okay. If you guys remember, I think from last class, I think it was on Friday. Yes, it was on Friday before our revision class. We have started talking about trees, right? Where I have shown you first the tree, then we have collaboratively discussed about what are the parts which a tree has, like root, branches, leaves, leaves. Yes, these are the three things which a tree has, right? And then I showed you also in the computers, or when we are trying to store any of the data, how can we use tree in similar way, right? Like if you guys remember about, like whenever we got any bigger problems, what is the best way to solve that problem? You guys have seen it a lot of time. What we do when we have a larger problem, we start solving. We divide that problem in smaller parts, right? First we like break it into two parts, then we break it into like, those two parts again, we break it into two parts, then we again break it into two parts, and then when we reach to the last part where we can easily solve it, from there we start solving it, and then we go back to the top, right? That's the way, like in real life also we do the same thing. Like if you want to construct a building, or like make like prepare a home or construct a home, you also start with that, right? You first go with the designing phase, you do the designing stuff, mapping, map part, all those things, right? Then you go for purchasing the resources, you go for other things. So you can see a bigger problem has been divided into smaller parts, then we have again divided it, and we again, like after dividing, we are trying to solve it. That's what you can see here. While we're dividing it out, that's again we are creating a trees, right? So guys, I think that's why trees, we can see it's everywhere, right? It's very important in the computer science as well. If you specifically talk about the computer science, we have discussed about the how we keep the data in our systems. There we also use the trees. Lot of like binary heap, or heap also uses internally data, tree as a data structure. The JavaScript object, they also use a trees. We have talked about in last class, right? When we were talking about the prototype chains. So there are a lot of examples which we had for understanding the trees. Okay, so already we discussed about trees a non-linear data structure where we play at a multiple levels, right? In a linear data structure, we just go into the straight line. Are we good with those things? Right, guys? We have already covered that part. What else we covered on that day? I remember we have also started understanding some of the nomination, the naming culture of the trees, like some of the things about the tea, some of the things about the trees. Like I think I remember it started with root node, right? Yes, Hariharan is saying root. Vishal is saying depth and height. Yes, Joseph. Yes, depth and height we discussed about, and I think we have discussed about the leaf node, and I remember internal nodes, right? Yes, leaf nodes are there. Siblings nodes were there, right? And child, discuss about the child node, parent node, right? And what else? I think subtrees. A tree can have subtrees as well, right? So those are, I think, let me share my screen and let's see. I think in the slides we have that topic. So we'll go there and we'll see that slide. So yes, as we can see, So this is the parent. These are all child nodes for that parents, and you can see here from one node we can go into the multiple nodes. That's why this is non-linear. It is not linear. That's why we say that tree is a non-linear data structure, and it also follows one hierarchy, right? If you know about your family tree also follows one hierarchy: grandfather, then father, then son, then grandchild, then the same goes, the same trees goes like that. So this is also, we say it right in the English words, we say that this is the family hierarchy. Same relate with tree as well. There we also have a hierarchy. Okay, let's see some more terms here. So root is there, right? Parent is there. For B, A is parent or his ancestors. Like these are the some same terms for parent and ancestors. And then descendant or child. Leaves less terminal nodes. Siblings are there, right? Anyone is still confused about the depth and height? We already talked about in the last class with examples about the depth and height. Guys, one more thing is here. I'm coming back to your question, Vishal, 1 minute. You can see here label as well, right? So right now they are representing label as a 0, but generally, I think in the slides also you can see. I'm not sure why they are representing like that, but if you go down in the label, you can see the label is 1 plus number of connection between node and root. So if you have calculated the depth, so just add 1 plus depth, that would be label. If you have calculated the depth at any position for any node, just add 1 plus there, that would be the label for that node. That's a simple definition for label. And that's what they are also saying it here, that 1 plus number of connection between the node and root. Or some in like I have seen in some places, if you want to find out the labels, they just simply say that 1 plus depth, and we have already calculated the depth. So 1 plus depth, that would be our answer for labels. How many children a parent at any level can have? At most. At most. If you talk about the tree, there is no restriction on that, Vishal. If you talk about a tree, simple tree, there is no restriction on that. Any number of children a parent can have on trees. There is no restriction on that. Yeah. If we simply talking about tree, then we can't have, there is no limitations. But there are some of the specific type of trees, like we are going to discuss it today, guys. There is very important type of tree which solves a lot of questions, and also in the computer systems, it use lot of times, like because it provides you very efficiently accessing your data or storing your data, because there is two things which we need to take care about: a data, how well we can store it and how easily we can access it. With the binary tree, there is one type of tree which I'm telling, that tree is known as binary tree. So binary tree has a restrictions, but before going into those restrictions, just understand binary tree is very important part of tree, which has been asked in a lot of interviews, and it really has been used in a lot of computer systems as well. Like there is BST, binary search tree, which is also like created with the help of binary trees. There are a lot of examples which you can see in the internet as well, and if I will also find it out, where you will see that a lot of things which we have created with the help of binary trees only. Okay. Before moving further, so Bishal, when we talk about that specific tree, there are restrictions. You cannot have like children, like many of children's like that, right? But yes, if you talk about the binaries, there is condition. I will tell you that. Yeah. Before that, can you, sir, Hariharan is saying, can you repeat label? So Hariharan, in the last class, if you remember about the depth and height part, so for finding out a label for any of the node, you just need to do 1 plus depth, and you will get the label for that node. Okay. Harijan, so like if we talk about that, let me see if in the node one node we have already Any of the where we are discussing about the trees? Oh, these all are the from the last class, right? Where we have discussed about the, yeah, I have deleted those notes. So let's quickly look into this. So this could be our root node, right? Then we have child like this. Correct? So now, so for depth, you guys remember that depth we start from 0, right? So for it, depth would be 0. For this node, depth would be 0, right? For this node, can anyone wants to tell the depth for this node? Yes, 1. Because there is one edge or link between root and that node. So depth would be 1 here. Same for this one as well. Depth would be 1. So level for them would be 1 plus depth. So this would be level 1 and this would be level 2. Same goes like this. If we want to find out the depth for this, so 2 would be depth here because two edges are coming between root and that node. Same goes here. This would be 2, this would be 2. So level would be 3 here. Understood, guys? About the label and depth? Label and depth, they have that relation. Okay. There is one more relation. I'm not sure, that would be height also. Okay. Want to know about the height? Okay, let's see. So if you want to find out the height for this node, anyone wants to give the answer? What would be the height for this node? What was the definition which I provided you? Level is calculated from depth only, or it can be calculated from height also. It can be calculated from height also. We can calculate from height also. We can create a relation. Let's see if we will find it out, the relation. Okay, if there would be, but yes, most of the time they say that you have to go with depth. You can see in the slides as well. Just read the definition of both depth and level. When you are calculating the depth, they are also saying that a depth of a node is the number of edges from the node to the tree's root node, like from the node to the root. And that's what same they are saying for level also. So level of a node is 1 plus number of connection between the node and root. So that's what I think for label, the best relation would be with depth only. Okay, understood, Hariharan? For labels, I think the best relation would be with depth only. Relation in the sense. Relation you understood, right, Hariharan, now? Okay, so Suraj and Hariharan was saying 3, 3 for that. So Vishal is saying distance calculated from the last node to the node where, yes, that's right. So from here, we have to go for the last node or farthest leaf node. Farthest leaf node. So you can see that how many there? 1, 2, and 3. So for this, height would be 3. Height would be 3. Okay, Suraj? Same for this one. You can see for this node, if you want to find out the height. So for this one, this would be 1. You can see just the one node you have to go. So you can see the height for this would be 1. Okay. Are we good with now the label and these things? No, no, label height is not calculated from root node. Height is calculated from the, if somebody wants to understand about the tree like height of a tree, so then you have to calculate from the root node to the farthest node. That would be height for whole tree. That would be height for whole tree. But they want to, if somebody wants to know height of any specific node, then this logic you need to apply. From that node, go for the farthest leaf node. Everyone remember that. Go for the farthest leaf node. Farthest means, like in Hindi we say सबसे दूर, like the most distance or the last node. That node you have to go and you will get the answer for height. Okay, that's what the definition says about it. Okay, guys, so let me see if I'm missing anything from the last class. Already discussed about the leaf notes, labels. We are good. I think in last class we have not discussed about the labels. That's why I bring it today. Surf trees, okay. Height, depth, yeah, fine. I think yes. Now we are good with the trees. Now we can jump into, guys, the next part, or types of trees. There are multiple types of trees. So we are going to start with the first and important type of tree, that is known as pine tree. Okay, guys, before moving that, anyone has any questions? Anyone wants a little bit more clarity? And I think, you guys remember in last class, I also told you that the trees, how like it, they somehow little bit closer to linked list. In linked list, we have one data, and then we have one what? The next pointer where we keep the address, right? In trees also, if you see this example, you can see this is one node. If you want to create a tree, we want to keep this. We have to create multiple nodes here, right? Already discussed, right? These all are nodes, correct? These all are nodes. Everyone agree? These all are nodes. Subtree, I think we have not covered it. Okay, I will explain you subtree also, but before that, these all are nodes, right? Yes, root also node. So definition of root is that node would be root which does not have any parents. That node would be known as a root node that does not have any parent. That's a root node, right? Height and depth of the tree same? No, they are not, Deepak. Height and depth are not same. We have already seen in the example. Height and depth of the tree. Okay, tree might be, let me see that. So if you talk about the tree, Deepak is asking about the whole tree. So let's see. 1, 2, 3, 4, and 5. So for this tree, height would be 5, right? And let's see the depth also. So for depth, from root node to the last node, 1, 2, yes. So for this tree, depth would be 5 also. Correct. For a tree, height and depth are same here. They will always be same. I need to check this thing. Height and depth. I believe height and depth should be same for a tree, because height and depth. When we create any room, also we say that we just say that height, it means something above a ground, right? And when we say depth, we say that something below the ground, right? In real words, we say that something below the ground. So that's why height and depth are similar. How depth is 5 for root node? No, 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 not for root node. Hariharan, not for root node. That's for tree, whole tree. Depth is for whole tree, not for root node. The height is for whole tree, not for root node. Okay. Okay. So before that, let's jump into the subtree part, which Vishal was asking. Okay. So Vishal, you can see this could be a subtree here. If we talk about this much part only, this could be a subtree here, because this particular part could be a subtree inside a big tree, right? This is whole tree. If we just divide this part, this could be another tree, right? So this another part of tree is called subtree. My marker is again hanging. Understood, Vishal? So the part of subtree, part of a tree can also be known as subtrees. So why we are talking about the subtrees? As you can see that, do you see a recursive nature here? When we talk about a subtrees, or you can see a tree can also have a subtrees. If we want to traverse it, does not it look like a recursive way? Like we have already traversed some of the tree, some like one of the part of tree, and we have to again traverse it. in a similar way the next part of tree as well. That's what the recursion means as well, right? We have already traversed some part of data, and then again we have to traverse in a similar way another part of data, but in similar way. And that's what in the trees also happening. They have the subtrees. We have to traverse in similar way. So that's what the subtrees. Whenever we talk about subtrees or anyone is saying about any subtrees, so they are referring to recursion strategies. They are somehow saying that you need to use recursion. That's what I believe. Okay, guys. So should we move forward, guys? Do you guys, if you guys still have any questions, queries, let me know in the chat. We can spend some more minutes here while understanding about the trees. Aras says nose. What about others? For Suraj, it's also clear. For Joseph, it's also clear. Can we call node 1 to last node a subtree? Can we call a node 1 to last node a subtree? If we talk about this node 1, if you're talking about if you're talking about this one, node 1, the straight line from node 1. This would be the last node here, a leaf node in the subtree. Understood, Visha? In that subtree, this would be the last node. In that subtree, if we talk about, so this would be, these two would be actually, these two would be the leaf node. This one and this one. Okay, Vishal? These two would be the leaf node, if you're talking about the leaf node. Yeah. Any more confusion, guys? Because yes, it's very nice to understand, right? Because we have to, because see, most of the questions which comes in the trees, they start with traversing a tree. How we calculate level? Level of tree is Deepak 1 plus depth of that node. Or if you're talking about the tree, so that then would be 1 plus depth only there as well. There would be 6 level. This would be level 1, level 2, level 3, level 4, level 5, level 6. Okay. So there are multiple types of tree, Hariharan. There would be any formula for that? I'm not sure, but there could be multiple subtrees. There could be multiple subtrees, Parag, there. Okay. And type of trees, if we talk about Hariharan, so we are going to start with binary tree, and there are I think ABL trees there, and there are red black trees there, and what about others? There could be like, yeah, B trees there, B plus trees there, ternary is also there. Vishal is saying ternary tree where uh, a specific node can have 3 childs or at most 3. Binary search, yeah, BST we are definitely going to see it. So there are multiple trees are there. We are going to start with binary tree. Okay, guys. So let's now jump into the binary trees, guys. Okay. Let me see if yeah, let's jump into the binary tree now. Okay. Yeah. So this is the binary tree, guys. So with the binary tree, there are very important conditions comes. One very important conditions. Now in this binary tree, they says that you cannot have many number of childs. You cannot have many number of childs. They are saying that you can at most have 2 childs. And when I'm saying at most, so guys, just understand the meaning of at most here. They are saying you can only have at most 2 childs here. And when I'm saying at most 2, it means you can have 0 child, you can have 1 child, you can have 2 childs, not more than 2. There could be one, yes, maximum. You can have maximum 2 childs. It means you can have 0 child, You can have one child, you can have two child. Could you please increase your voice a bit? Is it difficulty for you guys to hear me? Oh, 1 minute. Let me put. Can you guys hear and see me? Okay. Let me now share my screen. Yeah. Okay. So as I was saying, for a binary tree, guys, there is a one condition which they have provided. And the condition is you should have maximum two children. Any node can have maximum two children. Maximum two children means they can have zero children, one children, or two children. Some people say it as a, at most two children as well. At most and maximum. Okay, let me show you. Can this be a binary tree, guys? Can this be a binary tree? Let me know in the chat. Yes, because if we are considering this as my root node, then it has one child only. It has one child. So it is a binary tree. Okay, guys. Now let's check about this one. Can this be a binary tree? Can this be a binary tree, guys? Yes, because it has a two children, right? It has a two childs. So it is also a binary tree. Can this, if I have only one node, can this be a binary tree? If I only have a one node, can it be a binary tree? Yes, it can because it has a zero child. And that was our condition that there should be three type of childs, 0, 1 or 2. If I create like this, guys, you guys tell me, can this be a binary tree? Can this be a binary tree? No, right? Because you can see here, this particular parent has three childs here, and which is not acceptable. Which is not acceptable for a binary tree. Three child for binary tree, not acceptable. Correct? So this is not our binary tree. Let me see meanwhile the questions. Harihan is saying binary trees node can have almost two children. Yes, almost two children. The first tree must be in China, considering there is one child policy. Yeah, this which one? This one. Okay, okay. Arad is saying no. Okay, so for that answer. Okay, so this is about the guys. This is all the binary tree only provide one restrictions, and that restriction is this one only. You should have only 0 or 1 or and 2. These many child you should have, then you are fine. Then you can come under the consideration of binary trees. Okay, guys. So this is about the binary trees, and you can see, guys, if a node can max have only two childs. So what would be the implementation? If we talk about the like linked list implementation of or simply implementation of that node, implementation of node. So what would be that? What would be the field it will have? So definitely first field would be data, where we are going to keep some values here and two pointers, right? we are going to have two pointers. So where that would be left and right. We'll keep one value at left side, one value at right side. You can see that's what we are doing everywhere. If, okay guys, understood this thing first? Data left and right. Yes, we can say it's a double linked list. Yes. Yes. Everyone understood this thing? This could be the structure for a node in tree. For a node in tree. Everyone understood this? Let me know in the chat. Data left, right. In the data field, we'll keep the values. And in the left side, we'll keep the left node. In the right side, we'll keep the right node. Correct, guys? Okay, tell me if there are a root node which does not have any child, what would be these three values for that? Data, left, and right. What would be the value for that? What would be this node value? If we have first data, then left, then right. Yes, left and right would be null. And data would be 5. Everyone agrees with that? The node value for this root or just for one node which does not have any child? Everyone agree with that? Okay. What about guys leaf node? In every tree, we have a leaf node, right? Does they have the same structure? If I talk about 1, 2, 3, 4, does they have the same structure? Does they have the same structure? Leaf node? Yes, leaf node are the Nishant, leaf node are the node which are the last node which does not have any childs, which does not have any further childs, or the last node in our tree. Understood, Nishant? The leaf nodes, the last node in the trees. So will they have also the same conditions? Joseph says obviously. So everyone says that obviously here. That's right, right? Because they do not have any childs, they will have the same data. Correct? So that's what, guys. That's why I told you this. The reason for that is while you are traversing any tree, you should know where to stop. You should know where to stop. Yes, leaf nodes are unmarried. That's why they do not have any childs. Very nice, very nice. So guys, do you guys now like let's come back to the previous question. I know that was very funny joke. So what was that? What I was saying? Yeah. So did you guys understood this part? Where like while you're traversing any tree, where to stop? Like if you remember in linked list, how to stop in linked list? How to find out the end node in linked list? We just traverse it, and once we find it out, any node has a next as a null. Yes, node dot next is equal to null. That's the place where we stop it. In similar way, in a tree, how we will stop it? Wherever we find it out, left and right are null. That's the leaf node. Those are the leaf nodes. We need to stop traversing after that. Understand? I will explain it. We will show you with more example. Just I'm like ingesting this in your mind. But everyone like what like, I know that some more thoughts are coming there. How will I reach to this node or like that? But this is is this a possibility or not? Once you got left and right as the null, we should consider that this would be the place where we should stop our traversing. Understood, guys? Okay. Okay, so let's move into the next slide. I think there would be some more types of binary trees. So yes, they are just telling us about the ground, label, depth, height, which we have already talked about, right? You can just see it one for just 1 minute if you guys have any doubt in this. Can you like, you can check also, height and depth are correct here or not? Labels are correct here or not? Or is this a binary tree or not? First tell me, is this a binary tree or not? I think it's not a question because we are talking about binary tree. So, but yeah, I want you guys to think about is yeah. So everyone understand that it's a binary tree. Does it have the correct values of height, depth, or label? You guys check me and let me know. Does it have the same correct values of label, height, and depth? Anyone thinks somewhere it should be different? Okay, coming back to chat now. No, depth start from zero. Depth start from zero, Deepak. And label is depth plus one. Understood, Deepak? Label is 1 plus depth. And depth start from 0. You can see here, the first node here, depth is 0 and label is 1. So 1 depth plus 1. Are we good, guys? Now height, depth, label. Are we good with that? Okay, let's move into the next slide. Height, depth, level, they're just defining it. Okay, now let's come back to the next part, which is full binary tree. I also have in mind. See, this full binary tree is also known as one more name. So these are the types of binary trees now, guys. These are the types of binary trees also. Because sometimes some solutions could be more efficient with some of the types of binary trees as well. So that's why they have given some more, like they have just, you can see again trees coming again, like while we are understanding or talking about trees, they are also using the trees structure. So first tree, then they have branches out to binary tree, then multiple trees are there. Then in binary tree, they are again dividing it further to full binary tree. And what is the other name? Like almost complete binary tree or complete binary tree. These are just again the subtype of that. So that's what tree, like we are using tree on tree and tree, something like that we can say. Something like Inception movie, right? We're just going in one dream, then another dream, like that. That's what happening here as well. So let's now talk about, guys, this full binary tree, which is also known as strict binary tree. Okay, which is also known as strict binary tree. By the way, let's just understand all three: complete binary tree and perfect binary tree. Complete binary tree is also known as almost complete binary tree, and perfect binary tree is the perfect one. We will see what is the differences there, but just remember the name here. Guys, again, full binary tree is also known as strict binary tree. Strict binary tree. Sometimes people say that. Can you draw the strict binary tree? So you can understand. You have to think about the conditions about the of the full binary tree. Okay. Sometimes people say that I am not right now talking about the complete binary tree. So you can think about the. It's also known as almost complete binary tree. So that's what. Then we have perfect binary tree. So we'll talk about that as well. So now we are good with names. So now let's understand every of these types of binary trees. Okay, let's start with full binary tree. Okay, so you can see, guys, in the full binary tree, they are saying every node in a full binary tree should have 0 children or 2 children. That's the condition, guys, here. Okay, so let's come back to, so how two nodes are connected directly in compete binary tree. Let's understand his question. So how two nodes are connected directly in complete binary tree. I'm not able to understand your question, Nishant, but if you're saying how we are trying to connect two nodes, you can go back to double linked list, right? Not direct in graph, it just serial slide child. Oh, you mean in something you're talking about in slide? This is tree one, this is tree two. Tree two. Previous slides, okay. Previous slides. Yeah. In this slide, which one you're talking about? Okay, let me read your question again. How two nodes are connected directly to complete binary tree? Complete binary tree, yeah, this one. Oh yeah, this one you're talking about. This one, like two nodes, how these two nodes are connected. Right? Yeah, so left would be null for that node. Like this, I know there is confusion, no problem. If you're talking about this, Nishant, there was right? So for this, you can consider left is null, right has an value. For this, it will look like this. Data is 4, left is null, and right has a node 5, node 5, something like that. Understood, Nishant? Without any edge. Which one is talking about? Not sure, Nishant. If you can come to the you can come to the invite this part, the speaker part. We can talk about it. Which one you're talking about? Okay. Let's come back. By the way, go back to the next slide. Okay. Which was the full binary tree, guys. Okay. So in full binary tree, they are saying that FBT, full binary tree, they're saying that, guys, you can have only 0 nodes or 2 nodes. So you can see that in binary tree, we have one node as well. We can, like any parents can have 0 child or 2 childs here. But in the binary tree, we can have one child as well. But now you guys tell me, can this be a full binary tree or not? Can this be a full binary tree or not? You guys tell me in the chat. Okay, so meanwhile, I think Nishant has come to the speak. So let me invite him. Yes, invite. Yes, I've invited you, Nishant. Now you can talk about. Yeah.
Am I audible, sir?
1 minute. You are not. But yes, you are now. Can you?
Am I audible?
Yes, yes, you are. Let me come back.
सर सर मेरा जस्ट वो एक डाउट था कि लाइक ये दो नोड्स लाइक कैसे कनेक्टेड है राइट हैंड साइड पे कंप्लीट बाइनरी ट्री में लाइक
ये वाली
विदाउट
ना?
एनी एजेस हाँ ये कैसे कनेक्टेड
ये एज
पॉसिबल है
एज है भाई बीच में. दिस इज द एज.
ओह ओके
या. नो
तो
प्रॉब्लम.
वही डाउट था सर लाइक विदाउट लाइक एनी है जो कनेक्टेड है तो सो ये रॉन्ग नहीं होगा क्या सर
Definitely. Definitely there would be one edge always.
ओह ओके ओके कूल सर
Yeah.
थैंक यू
So not perfect binary tree. Not perfect binary tree. No, no, we are talking about right now this one, full binary tree. Okay, full binary tree or strict binary tree. So will be a full binary tree or not? So this will not. Why? Because it has it one child, and that was our condition that the full binary tree should not have any node which should have one child. It should. If I create one more child here, now it will be full binary tree. Understood, guys? Now that would be full binary tree. Okay, so not perfect binary tree. Perfect, we'll talk about the perfect binary tree, Joseph. So trees are used in which cases? There are many cases actually, Hariharan. If you will think about in real scenarios also we use trees on many places, and in the computer systems there are many examples like min heap. A lot of things are internally implemented with the help of trees only. Okay, like if we just simply talk about that b tree is there, b plus tree is there, which provides all the important data on the leaf nodes. If we just talk about the b plus tree, while searching and while traversing, these all tree structures provides your accessibility little bit faster. Because if you talk about the linear data structures which are array stack, you can just search in one way. But with the tree you can search parallelly. And you can go into the multiple ways. Correct. So that's what the benefits of we, which we personally feel that we can go into multiple ways. Okay, so this was guys about the full binary tree, or also known as strict binary tree. I think in my neighbors still they are celebrating Diwali, so a lot of you guys can hear it, right? Yeah, happy Diwali, guys, everyone. No, 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 someone is not beating. These all are patake and all these things are happening. Okay, so now now let's move into the next part, guys, which is the complete binary tree, or almost complete binary tree. Yeah, this one, almost complete binary tree. So they have provided two conditions to you for almost complete binary tree or complete binary tree. They have provided you two conditions. First condition is that all labels are completely filled except the last label. All labels are completely filled except the last label. And then they are saying whenever we are adding a new data or key, it should always be preferred left side. It should always be preferred left side. So let me show you what they want to say that. All like a complete binary tree and almost complete binary tree. It's also known as almost complete binary tree, right? So they are saying the first condition, guys, which is only the last label should be, that was the condition, right? All labels are completely filled except the last label. Correct. So you can see this is the label 1, this is the label 2. Let's try to design it. This one, this one, this one, okay, and this one, hmm, and this one. Correct. Hmm. Okay, yes. And this is the label 3, and I think this will be level 4. Okay, so I think let's now talk about the two conditions, guys. So the first condition they are saying all the labels should be filled. All the labels should be filled. 1 minute, guys. uh, just 1 minute, guys, let me think about one more thing. Yes, so you guys tell me, is it matching the first condition or not? The first condition is all the inter label should be filled. Then only we should go for the next label. Or only the last label should not be filled. And then all internal labels should be filled with childs. There should not be single child. There should be always two childs. And then the second condition is that we should always prefer to insert left side, then we should go for the right side. So according to those two conditions, you guys tell me, is this the almost complete binary tree or not? Is this the almost complete binary tree or not? Yes, yes, yes. Everyone is saying yes, yes, yes. So we're saying yes. So I think, guys, first let's check for the second condition. The second condition is we should always fill data to the left side. But you can see here, as I'm filling this data for this node, I am filling at the right side. I am filling it at the right side. So definitely this is not going to be almost complete binary tree, or this is not going to be complete binary tree. But what about the first condition? Is it fulfilling the first condition or not? You guys tell me. Is it fulfilling the first condition or not? It satisfied the first one. Oh, yes, I believe it satisfied the first one because all the internal nodes, all the internal labels are already full. All the internal labels are full. It's just the last label which does not have any elements, which does not have any element. Correct. So I believe The first condition is satisfied here. Okay, let's see one scenario where the first condition would fail. Where the first condition would fail. I have example for that, and that would be this one. I have the in my copy. I have that example. Yeah, this would be the example where you can see that this is level 1, this is level 2, this is level 3, and this is level 4. As you can see, before the last level 2 is already empty, right? And this is not acceptable. This is all not also not almost complete binary tree. Correct? You can see that last label is 4, but internal labels are also not filled. So that this is also not almost complete binary tree. Guys, you guys tell me, is this the full binary tree or not? Is this full binary tree? Both. Tell me for both. Both are full binary trees or not? Tell me, both of full binary trees or not? Can you repeat? I got disconnected. 1 minute. I just ask one question, Nishan. We will explain it. Second one is who was saying that? Vishal is saying second one is Vishal. For the condition, the full binary condition is you can have 0 child or 2 child, right? What about this one? What about this one? Yes, so both of these two trees, I can see that they have this one element. So though both are not full binary trees, and both are not the almost complete binary tree. They both are not almost complete binary tree. They both are not complete binary tree. Okay, guys. Okay. So for Nishant, okay, Nishant, what I explained about the complete binary tree or known as almost complete binary tree, which is that it should have two conditions. The first condition is all the internal labels should be filled. All the internal label should be filled, or people say it in another way, which is I have written here. When label is full, when any label is full, then go for next label. When any label is full, then go for next label, except the last one. You can see when the third label is full, then only I go for the fourth one. When the second label is full, then only I went for the third label. So that's what the condition is. When all the internal nodes, all the internal labels are fully filled, except the last one, that could be almost complete binary tree. And the second condition is, Nishant, that whenever we are filling any of the nodes, you can see whenever we are filling any of the child nodes, it should always prefer the left side first, not the right side. If they are only filling the right side node, not the left side, that will not be almost complete binary tree or complete binary tree. That's the example. Okay. In complete binary tree, also check child 0, 2. Yes, in complete binary tree 0, 2. Yes. 0 only for the last node. All the internal nodes should be 2. Okay, Suraj? All the internal nodes should be 2. 0 only for last node, leaf nodes. Or the last label. Last label. I think last label would be the better word to use here. Okay, guys, so now let's go for the perfect binary tree. Now let's go for the perfect binary tree. All internal nodes have 2 children and all leaves are at same level. All leaves are at same level. That's the perfect binary tree. It means, guys, all nodes should be fully filled and all nodes, all the leaf nodes should be at same level. You can see this is level 1, this is level 2, level 3. That's what they're saying. All the internal nodes have 2 children and all leaves are at same level. You can see all leaves are at same level. So this is our perfect binary tree. That's what they're saying, right? Yes, perfect binary tree. And some people says this also complete binary tree. Those people called this tree as a almost complete binary tree, and those people called it as a complete binary tree also, or perfect binary tree as well. Which where all the internal nodes will have two childs, and all the leaf nodes are at the same level. 1 minute, guys. Understood, everyone? Full binary tree, perfect binary tree, complete, almost binary tree. All complete slash almost complete binary trees can be perfect, but not vice versa. All complete slash uh, almost complete binary trees can be perfect. Hmm, not sure. Let's see that. No, actually, that's wrong. Because Arad, you have seen that, right? In the complete slash almost complete tree, we have seen single child as well. We have seen the single childs as well. But in the perfect binary tree, we have seen that we should have the the internal one. If we have to fill, if we have to fill, we must do it from right side, right? If we have to fill, we must do it from right side. Uh, that's not like mandatory condition for for the complete binary tree or almost complete binary tree. The condition is you should always start filling from the left side. Okay, start from the left side. Perfect binary tree is always symmetric. Can also be symmetric. We can say that. Yeah, it might be symmetric. Yeah. Yes, I think totally right, Parag. Because they're saying all the internal nodes should be uh, the the two child. They should have two childs. So always they will be going to have the two childs, and all the leaf nodes should be at the same label. So yes, that is going to be symmetric. Now the perfect binary tree can also be full binary tree. Can be also full binary tree, right? Uh, Perfect binary can also be a full binary tree. Two childs or zero childs. Yes, perfect binary could be full binary. Yes, yes, yes. Could be. Full is equal to perfect. Perfect is not equal to full. Full. If there is any full binary tree, that could come under the perfect binary tree. Mm, no, that's not right. Because see, this could be a full binary tree or not. Let's see. Is this the full binary tree or not? Is this the full binary tree or not? It is right. It is right, but it is not perfect binary tree. It is not perfect binary tree because all leaf nodes are not at the same level. Perfect can be called as full. Full can, yes, that could be yes, yes, yes. Perfect can be called as full. Full cannot be perfect. Yes, yes, yes. That might be right. Perfect, I think, could be called as a almost complete binary tree also. Let's think about it. So the almost complete binary tree condition was all the internal nodes should be filled and leaf should start from left side. Yes, like there could be some scenarios um, where It could become perfect as well. So yes, I think perfect is the master one, which could have everything. And then we have the remaining parts as a full binary tree and the uh, almost complete binary tree. So let me just revise it as Joseph wants again. So Joseph, for the full binary tree, you should check only one condition. Almost it should have zero child, no other condition. Zero child or two child. This is the condition for full binary tree. Sorry, for this one, sorry. Full binary tree. Zero child or two child. That's the condition for full binary tree. For almost complete binary tree or complete binary tree, the condition is if there is a single node, that should always be inserted from left side. So you should remember left side, comma, all internal nodes should be filled. Internal node should be filled. This is for the almost complete binary tree or sometimes complete binary tree. For the perfect binary tree, all the internal nodes should be filled with two childs. All the internal node should be filled with two childs, and leaves node, last or leaf node should be at same level. Should be at same level. Hey, I remember one question actually. Somebody was asking in the almost complete binary tree that all the internal nodes should be having a double child always, or they can have different childs as well. So I'm thinking about that one. Let's think about it, guys, because in the perfect almost in the almost complete binary tree, they are not telling it like all the internal nodes should have two children only. You can see in the perfect binary tree, they are saying it all the internal nodes should have two children. But let's think about here in the almost complete binary tree. They're not saying it. They're just saying that all labels are completely filled except the last label. Does it mean that all the labels before the last one, it should have two nodes completely filled? I think yes. What what else could be the meaning of completely filled? I think yes. All the internal nodes should be all the internal nodes should have must have two childs. Yes, I think yes. When they are saying completely filled, it means we should have two childs. Yeah, but there could be scenarios. Yeah, I think the almost complete binary tree and binary tree could be in difference, because in the almost complete binary tree, they are not saying that the all the leaf nodes should be at the same level. All the leaf nodes should be at same level. So that could be the difference between almost complete binary tree and perfect binary tree. They're not saying that all the leaf nodes should be at the same level. So that could be the difference between almost complete binary tree and the perfect binary tree. Except leaf, yes, except leaf. Okay, guys, are we clear in our mind? So for full binary tree, what is our condition? For full or strict binary tree, our condition is zero node or two child, zero child node or two child node. That's the first condition for full binary tree. Now second binary tree, almost complete binary tree. Two conditions are there. First condition, all the internal nodes should be completely filled except the last one. All the internal labels should be completely filled except the last one. First condition. Second conditions, whenever we are inserting a new key, it should always be preferred to left side. Always be preferred to left side. That's the two condition for almost complete binary. Third condition, for the perfect binary, it's all the internal label should have two childs. All the internal labels should have two childs, and the leaf node, all the leaf node should be at the same level. All the leaf node should be at same level. Okay, guys, that was the three different type of binary trees. And what about the binary tree? What is the condition for binary tree? It could have zero child, one child, and two child. That's the condition for binary tree. So are we good with these 4 binary trees which we talked about? Are we good, comfortable? Will we remember these things now? See, perfect is very easy. Perfect is like symmetrical one. We are not going to leave anything. Two, everywhere 2 nodes. All the leaf nodes should be at the same level. That's the perfect one. Almost complete, almost perfect. It means it's just leaving it at the leaf side. Almost perfect, almost completely binary. It's just leaving us at the leaf level. Otherwise, all the internal levels are already fully filled. That's why we are saying almost complete, because we are leaving at the leaf node. And for the full binary, we are saying it should have only 2, 0 or 2, full. We should just do the full, 0 or 2. Full, complete or perfect are binary trees. Yes, these are binary trees. These are types of binary trees. Okay, guys. So let's now implement it. Let's now implement it. I think we already know the implementation of it, but let's see what else is there. Yeah, let's now talk about the implementation of binary tree. Are we good? Can we move further? Or anywhere you guys is stuck right now? Let me know. Anywhere you guys are stuck right now? No, right? We are good. Okay. So let's now talk about the implementation, guys. So I think we already seen that we have to create the nodes here. We have to create the nodes here. And now when we are creating a nodes, what is the best way to store that? Now we talk about the storing part. What is the, like, not the best, just tell me about what are the ways to store that nodes. When we talk about the queues, there was only 2 ways. When we talk about the stack, there was only 2 ways. Same goes for trees as well. What are the 2 ways, guys? Arrays. Okay, yes, array is the by default one. We can keep these nodes on arrays as well. Linked list, yes, second one is the linked list. Double linked list, yes. Okay, so that's what, guys. These are only the 2 ways, and I think the mostly people use it the double linked list one, where they just create the nodes and they just use it like similar way, right? In the left side they will keep it. I will show you that. I will show you that. Yeah. Okay. So you can see here, guys, that we have fair idea about the binary tree. If we talk about the implementation of it, so we can use the nodes. We can implement the nodes using, we can implement the tree using nodes, which is store the information about the current node as well as the information about the child nodes, right? And those child nodes are left and right, which we talked about, right? Here, if you guys remember, where we were talking, yeah, this one, left and right. These are the childs, correct? And the another way is they are also telling you about the another way, which is the using arrays. Like in the because see, in the linked list we are good. In the linked list we are good because in one node we have 2 pointers. We can easily go to the left and right side. But with arrays, it's a problem. We have to find it out for any particular index where we have to go for this left or where we have to go for the right. Correct, guys? In the linked list, when we pick any node, that node already has the information. In the linked list, that particular node already have the information. Am I right, guys? In linked list, it's easy, right? We can go to the child, left and right, easy. But in the arrays, it's little bit difficult, right? So that's what they have suggested one idea. In the, if you want to store a tree or implement a tree with the arrays, so you need to use this logic: 2i plus 1 for left node and 2i plus 2 for the right node. And for at the ith index we will keep our main value. Like if we talk about this one, like there is root node and there is 20 and there is 30. So what we will do, like we will take, this is our first value in our array. So we'll keep it as the 0th index, at the 0th index. And then for left and right, we'll do 2i plus 1 for left and 2i plus 2 for right. Correct. So 2i plus 1, what would it give us? 1. So at the 1 index, we'll keep the 20. And here if I put it, so at that second index, it will give us 30. Now for 20, if now this 20 has any child, 40 and 60. So now again, we'll do the same calculation here. 2i plus 1, which would be 2 multiply 1 plus 1, which will give us 3. So now at this index, 40 will come and here 60 will come. You can see this is the perfect logic. 2i plus 1, 2i plus 2. It will continuously increase your values like that. Now goes for 30 as well. 50 and 80. Same logic will work. This will give us 5 position for 50 and 6 position for 80. So 2i plus 2, 2i plus 1, it is going to, and this in this similar way, we are going to traverse it. But it's like I have not used it. In the interviews also, I have not used this way to store the to store the trees. I have always used uh, the first one, the linked list one. If no child, then index will be null. Yes, if no child, then index will be null. Yes, if there is no child, then we will keep the index as a null there. Okay. Farah, they have given us formula for 2i plus 1 would be the position for the left child. 2i plus 2 would be for right child. There is one node. It has left and right childs, right? So now they are saying that 2i plus 1. Yeah, I'm repeating it, Arad. I'm repeating it. So if there is one node which has two child, right? One is, so the first child is root node, there is one child, there is one node which is a root node, right? Which has value as a 10, right? And now we have this particular root node has two childs, 20 and 30. So you want to store this 20 and 30. So the position they are suggesting for that particular node where you are storing 10, take that index and use 2i plus 1. At the 2i plus 1, whatever index you are getting, you will be getting the left value, left child at that place. And 2i plus 2, at this position, you will be getting the right nodes for that. And that's what's happening here as well. You can see 10 is a root node. So we are starting from 0th index in array. This is at 0th index. So you can see at 0th index, I kept the 10 here, right? And then for keeping its childs, left and right child, I have used this formula, 2i plus 1, 2i plus 2. And it is, you can see, it is giving us one index and second index. So at the first index, I'm keeping 20. At the second index, I'm keeping 30. If these also has a child, so again, we'll consider it as a subtree where 20 would be a root and 40 and 60 would be their child. You can see I'm using the same formula again, 2i plus 1, 2i plus 2. And that's continuously goes on. But we are not going to use the array way. We are going to use the linked list way. Okay. So guys, the insertion part, we'll talk about it later when we talk about the binary search tree. But let's not talk about the traversing part first. Okay, which has been asked to me in also in many interviews. So right now I will say that if this is my any of binary tree, if I'm talking about, let me know if this is a binary tree or not. I'm just putting any random values here. Is this a binary tree or not? You guys tell me everything, like binary tree, full binary tree, almost complete binary tree, and perfect binary tree. Tell me all these four. Put it in your answer. Just look into this one and tell me now. I hope everyone has seen it. So now I'm coming back to chat. Yes, no, no. Okay, Likit is saying yes, no, no. Some people are saying yes, no, yes, no. Almost. Guys, give me the answer in the as Likit is giving. Yes, no, no, no. That would be better, right? Hariyanan, yours is fine. You don't need to give it now. But for others, as Vishal and Likit, they are giving. So definitely, guys, this is the binary tree. This is going to be yes. Because you can see everyone has 0 or 1 or 2 childs, right? So definitely it is going to be binary tree. Let's look about the full binary tree. So full binary tree says it should have 0 or 2 childs, which is not the case here because we have the 7 here. So definitely it is going to be false. Now let's talk about the almost complete binary tree. Let's see, is it the almost complete binary tree or not? First condition was all internal labels should be completely filled. So all the internal labels are completely filled. That's totally right. The second condition is always if we are inserting the new one, it should be on left side. So yes, it is. So definitely this is going to be yes. A perfect binary tree, definitely not, because all the leaf nodes are not at the same level. So whoever is given this answer, yes, false, that was the right answer. Yes, no, yes, no, yes. That's the right answer. Okay. Okay, guys. So now we'll talk about the insertion. We'll see later, guys, how to insert. Because I think explain full. Explain full two condition. No, full has only one condition. That is, you should have 0 child or 2 childs. That's a full complete binary tree. An almost complete binary tree has two conditions. The first condition is all the internal labels should be completely filled. All the internal labels should be completely filled except the last one. Except the last one. And second condition was if you are inserting any new elements, they should be always be in the left side, not on the right side. That was the second condition. And both conditions are matching here. You can see 4 is at the left side, 7 is also at the left side. We can change this 7 because we already use this 7. So we can use it 9 here. Yeah. Got it? Suraj now? Two condition repeat. You have mentioned it earlier or? Sir, the second condition must or most possibly we need to insert it. Yes, that's a must condition. Both conditions are must. All the internal labels should be filled and always the new node, whichever is inserting, it should always be on the left side. Second condition repeat. Always the new node should be at the left side. As you can see here, always the new node which we are inserting, it should be on the left side. If we talk about this one, Suraj, this is now not correct. This is not the almost complete binary tree because we are inserting a one new node here which is on the right side, which is not correct. Got it now, Suraj? It should always be at the left side. Okay, guys. So yeah. So can anyone wants to tell me insertion would be easy right here? Insertion would be easy. Like if we just take the first node, traverse to the left, insert it there. Insertion we'll talk about the in the binary search tree. Right? There would be insertion would be, you will understand why I'm not talking about it right now. So there we will talk about the insertion part. Okay. So first let's talk about 1 minute, guys. I've opened the Slack. 1 minute. Let me close that. Yeah. So now let's talk about traversing. Traversing means I want to traverse all of the elements in binary tree or in my tree. Right? I have one tree and I want to traverse whole of that tree. Traverse means just like print all the nodes or all the values which are present in the tree. Okay. Yes. Similar like iterations. We have to just iterate whole tree and print the values there. Understood, everyone? The traversal part or iterations. Generally, we say it as a traversal. Okay, when we talk about the trees, so people generally take the name of traversal. Traversal means just traverse or iterate, or just go and go in that tree and check all the nodes values. That's what the meaning of traversal and iteration. Are we good with traversal and iterations, guys? Everyone? Understood the traversal iterations meaning? Okay. There are two ways, guys. There are two ways to traverse in a tree. First known as DFS, second one known as a BFS. The full form of DFS is depth first search, and the full form of BFS is breadth first search. So DFS and BFS both has their own differences, and we will see both of these differences, how the traversing happen in both of the scenarios. Okay. Now under depth first search, there are three more traversal, which are known as pre-order, in-order, and post-order. Okay, and in breadth first search, there is only one traversal, which is known as level order traversal. That's why breadth first search, also known as level order traversal. That's also known as level order traversal. So everyone has to remember these things. Sometime in the interviews, people ask about it. They ask it how many ways we can traverse a tree. So you will say that we have only two ways to traverse a tree. Traverse a binary tree, and that traverse those two ways are DFS and BFS. In DFS, the full form is depth first search, and in BFS, it's a breadth first search. And in DFS, we have a we have three more. I have a doubt in my previous question. I think my answer is right. Yours one, what was your answer, Likit? You're talking about this one. Is it? It is not a complete binary tree, but you can see all the internal labels are filled, and we are pushing it from the left side. Is it there anything else we have to check for in the complete binary tree? Are we missing anything? Lick it there. Child must be left side. Oh, yes, these are child all of the left side. You can see all the childs are at left side. Full left must be filled. Full left must be filled. You mean all the nodes should be having the left node? That's what you're saying. All the leaf nodes should have like that. You're saying. Okay, let me check into, guys, if that's the condition for that. Complete or like what do you say? Almost complete binary. Let's see the definition here. Or is there way to check? Check almost complete binary check. Almost complete binary examples. Mm. Okay, let's see there in the one of the articles. Tree is there. Okay, complete, almost complete binary. Yeah, this one. Let's see. So insertion node must take place level by level. Okay, and all the nodes must be left justified from left to right. Okay, so all the nodes must be left justified. So it means that like all the nodes should be filled with left node from left. All the labels from 1 to n minus level and its n to number of labels should be completely filled without any gap. Okay, that one is from the for the internal nodes. Important point is that if a node at label h, where h equal to 1 to n, has a right child, then it also has a it also has a left child. Okay. Here, the symbol almost is trees left tree is correct example of almost. Tree and right tree is incorrect example of almost tree. That one is fine. What about this one? No tree is community till maximum level. But here you can see Alikit, they do not have any element on the left side, right? And they are saying this is almost complete binary tree. Okay, it's not. It's not a complete binary tree. You're talking about the perfect binary tree as a complete binary tree, Likhit? Because we are only talking about the 4 binary tree here, right? Almost complete binary tree, perfect binary tree, and the full binary tree and the binary tree. Understood? Okay, we can. Yeah, so that's what they're saying. Almost complete binary tree. You see here, they are leaving it as the last element. Okay. Okay, guys. So let's move further. Let's come back to the DFS and BFS, right? So as you were talking about the DFS and BFS, so in DFS, as we know that there are 3 more ways, which is pre-order. Sure, Likhit. We'll check that, and if I had any other discussion here, I will post it in a LinkedIn. Okay, we'll discuss it about there further. But that looks like whatever we are right now talking about, then those all are correct. But yeah, we'll see that almost complete vanity. We'll see again. Okay. So let's move into the next topic, guys, which is the traversal part. So on the traversal part, as we know that there are 2 type of traversal, which is DFS and BFS. In DFS, we have pre-order traversal, post-order traversal, and in-order traversal. And for the BFS, we have a level order traversal. Okay, you know, guys, how I remember it in college. Let me first start with the depth first search. Okay, let's take the same example, right? Yeah, this one. So guys, in the depth first search, whenever we talk about the depth, right? So while we traversing this tree, we first go to depth, and then we start going back from there. So right now you can see the depth is this, right? The maximum depth is here, the last. Correct? If you want to find out the depth of this element, what would be the depth of this element, guys? Can anyone wants to tell? What would be the depth of this element? 3, right? It would be 3. So that's the maximum depth, right? That's the maximum depth. So that's what? From root, we always start traversing from root. We always start traversing from root. We first go to depth, fold depth, and then read that particular element. And then we start going back from there. Then we will go into this one, in this subtree, because it does not have any other child. We'll go above. We'll again read it, all the elements from here. So what I mean to say here, whenever we are talking about the depth first search, we first directly go into the depth of that tree. We do not start reading from the top elements, something like that. We always first try to go for the depth size, and then first we start reading from there. But in the breadth first search or level order traversal, we do not go directly into the depth. We start reading from here. Then we'll go into the next level. Whatever elements are there, we will read into the whatever elements are available in that level. Then we will go into this one. We will read into whatever elements are available in this level. Correct? And then we go for this one. We'll read into the elements which are in this level. So that's the difference between DFS and BFS. In the BFS, as you can see, we are reading level by level. Level by level. But in the DFS, we first directly go into the depth. And from depth, we start reading it out. Then we go back. Then we go like right side. We go like that way. So it means first we directly jump into the depth, and then we start coming back to up. You guys understood the difference between the DFS and BFS? Most of the scenarios, most of the places we are using BFS, but there are some of the problems which we solve with DFS also. No, it depends on scenarios, guys. It depends on scenarios. But yes, most of the time I have seen we use the BFS. Most of the places we are using the BFS, but there are some problems. I think there is like a closed island or Island 1. These are some of the problem in lead code where we use DFS also. I remember. Or connected components in graph also. You know, graph is also like one type of tree. Graph, if we just will move into the graph, I'm not sure, but graph is also one type of tree, right? So, or we can say tree is a one type of graph. In the graph, we can have cycles as well. Like right now, you can see tree does not have any cycles here, but in graph, these could be connected. These nodes could be connected here in the graph. If we just connect this node, this will become graph now. Yeah. So that's why while we traverse the graph also, so we use BFS and DFS there as well. So, but BFS has been used most, which I have seen that. A lot of like shortest distance problem. Wherever I am seeing shortest distance problem, we always use BFS there. Shortest distance problem between point A to point B. Always we see that BFS there. Okay. Top to bottom and left to right. Yes, top to bottom. First we go into the bottom, then we start coming up. Okay. And guys, now in the because see in the level order traversal, we just we are just like going into the labels and just traversing those elements. But you can see in the DFS there is one problem, right? In DFS there is a problem. You have to decide which direction you have to go. Like this is 2, this is 3, this is 5, this is 6, this is 7, this is 8, this is 9, and this is 4, right? So now once you reach to depth, once you reach to this depth, so now you have only one element here. Okay, you have read the 4, I'm fine. Now you went into the parent of it. You only have again one element, no problem, right? But once you reach to this place, you have to decide. You have to read this one or you have to read this one. Correct, guys? You have to decide. You have to read this one or first you have to go to this one, the sixth one. Correct, guys? In the DFS, we have to decide sometime which element we have to read. That's why DFS has 3 types. That's why DFS has 3 types, guys. And these 3 types are these: pre-order, in order, and post order. And you know how I remember it? Wherever pre is coming, root will be first, in order, root will be in the middle, in post order, root would be at last. And then left and right. Sorry, then left and right. Then let me take the another color for that. Then left and right, left and right, left and right. You can see this is the root element. You can see in this subtree, see every node always has 3 things. Every node, if we talk about this one also, every node has 3 things always. What are these 3 things? You tell me. What are these 3 things every node has in tree? Root, left, right. Yes, root, left, right. You know that in the previous slide, we have already discussed about it. All those 3 things. Yeah. Here you can see. Yeah, this one, data, left, right. Data, we are saying it as a root. Correct? So every time, yeah, data, left, right, or we are saying that a single node itself a root. A single node itself a root. So that's what in pre-order, in when we are traversing in pre-order, so always first root will be printed. So first 2 will be printed, then left 5 will be printed, then right 6 will be printed. But if we are traversing in order, this is pre. But if we are traversing in order, then first left will be printed, then root will be printed 2, and then 6 will be printed. And if we talk about post, then first left and right, so 5 comma 6 and then root. You can see root is it come. You can see I'm just circling out the root according to here, according to these formulas. In my college, actually, I remember like this. Wherever pre is coming, pre means first. So root will come as first. In order means middle. Root is coming at there. In post order means last. Post mean after. So root will come at last. And that's how we do the traversing here. I hope you got little bit idea, guys, about the. Yes, we are going for the break, and after that we'll see the examples of these. But yeah, let me repeat it also, and then we'll go for break, and then we'll see some examples of these traversing in order, pre, in, or post. Okay. How do we sort the tree? Good question, Ankit. We'll talk about it. I think this question could come in our problems. Okay. So BFS, are we good with BFS first? Tell me in the chat. Are we good with BFS? Are we good with BFS? In BFS, we have to traverse elements and level wise, right? But now let's talk about the DFS. In the DFS, there are three ways: pre-order, in-order, and post-order. Okay. And I was explaining you guys each node. If we talk about a single node, this node could be a root node, right? Because it does not have any childs. All childs are null, right? So this is a tree. We'll just consider this as a tree, right? So now if you want to do the traversal here, so we always follow this way: root, left, right. And if we simply talk about this element or this tree, 5, 6, and 7, you see the same structure here as well. If we are at the node 5, we have one left, one right. If we are node at node 4, we have left and right, but those are null here. And the element, the which element we are right now checking, that would always be known as root for that tree. Root or parent, right? For that tree only, not for whole tree. For whole tree, this is the root node. But for this tree, this is the root. This is the left and right. For this tree, I already told you, right? This could be one tree. You have to put root as a first element, then left and right. In order, you have to put root at the middle. In the post order, you have to put root at the last. And then we have shown this example with this small tree, with this small subtree, where 2 was root, 5 and 6 was left and right. This was a root, this was left, and this is right. And then you can see in the pre root should come first. So root is coming first, 2, then left, then right. In order, root should come into middle, and then left and right. And in the post order, root should come in the last, then left and right. Understood, guys? Audio and video is stuck. Is it happening with everyone? Okay, guys. So let's go for break, and then we will see some examples of traversing of these three, and then we'll see the. Can you guys see me? Might be internet. I will check in the break. Yeah. Okay, guys. So let's go for break. It's a 9:42 right now. So we all can come back at 9:57. Okay, 9:57, 9:58. Okay, guys. So let's go for break. We'll talk about it, Hariharan, after break. Okay. Is everyone back? Can you guys hear me? Great. So let's just wait for one more minute. Then we'll start seeing our example. Oh yes, Likit, actually. So yes, I have seen this example. Now when I went for a break, so I was just looking into this one. That's fine, Ariran. I just drank some hot water, so that's fine. So yes, actually, the point which Likit is trying to make. Oh yes, that's very interesting news. Actually, today, my and my colleague in PayPal has talked half an hour about it, so we definitely know about it. And after that, what he is doing, not sure results was bad, but yeah, that's another topic. Yeah, he has fired, or he has given, the recent news. If if you're not implementing it in till 7th November, then he will fire. Like he's giving the direct warning. So that's not good actually. That's not like employee culture. So let's see. So sometimes people says that like sometimes terror or fear is the one who motivate others to create their own things. So not sure about it, man. It's in danger or not? Because see, the Elon Musk has come with lot of big organizations for Twitter only. He has bring blockchain Beyonce also. I was just reading the news. He has brought some good ideas. Like when he has given that much money to Twitter, so he has taken some money from some other organizations as well, right? So he has taken money from some different organizations. We can you guys hear me? Yeah. So they also have that, right? The bot which Musk has brought it, and the Twitter also has a lot of political influence. So let's see. That's another day topic. We can talk long about it. Yeah. So let's come back to the previous thing, where I think yes, I want to correct one thing which Likit was trying to say from very long back. And guys, what was that thing? Let's come back to our example again about the absolute complete binary tree. And the, guys, 1 minute. Yeah, can you guys see my screen? Yes. Yeah, actually, I told to my younger brother, to check it. Something is happening with Wi-Fi. But yeah, can you guys hear me now? So let's back to this example. So actually, the problem, what is here? The problem is, so in absolute complete binary tree, we were saying that always a new element should be filled from the left side. We were saying always a new element has to fill from left side. Am I right? That's what I'm saying till now. Right, guys? That's what I'm saying. But you can see this element 9. this element, this 9, is not from the left side. If we just go a little bit above to 8 and go to 3, you can see this is coming from the right side of 4. This is coming from the right side of 4. Correct? This could be condition correct once we have the here also like 10 and here also 11. Then this 9 could be correct. Understood, guys? What Likhit is also trying to say from that time? This is not not coming from the left side, because all the left side of it me. Actually, yeah, I know. I think something happening with my internet. Okay, okay. Thank you. Let's take the slide of here. Let's try to understand here. Okay, might be if my internet is problem, then it could become problematic. No, actually, Likhit, that's right, right? All the left side. That's what I read it in here. That all the left side should be filled. Then the right also must be filled. But they are saying that the left side, right? Because they are saying at the last label, then at the last label, left block, yes, right should be filled. Okay. Okay. Then okay, I think let me clear it out again. I might have missed that part. And let me read it again, okay? Because what I understood with that, they are saying that all the left should be filled first. Then it might be possible that let me read it, okay, guys? For the absolute complete binary, let me read it again, and then we'll again discuss about it in the next class. Okay? Might be I'm missing some of the thing in the terminologies. I will see some more examples, and then we'll talk about it. From left must be filled, not only left. Okay. Sure. We'll look into this example. Okay, guys. So absolute complete binary tree, we'll see some more examples, and then we will confirm this thing that only left is there, or from the left all be must be filled. Correct? So like right now, Likhit is saying that if we are talking about the left, so right should also be there. Then it is good. Right? So this could be the possibility. He's saying that we need something here as well, like 8. And then this could be the absolute complete binary tree. Okay? So that's what we'll see, that is this the correct, or only left is also fine. Okay, so we'll see that from tomorrow in next class. I just read it quickly, so I just understood this part, left part. Okay, guys, so let's move into the next part. Okay, guys, so we will talk about it again tomorrow in our next class. Okay, so now let's talk about the traversal part quickly, guys. So we have started with two type of traversal, which was the first one was the depth first search, which was the DFS, and the second one was the BFS, breadth first search. So let's take one example and let's try to implement all four, right? Because in depth first search we have three traversals, right? Pre-order, post-order, and then we have the last one,
the post order as well. Sorry, pre, post, in. Sorry, I was missing the in. So pre, in, and post order. And in the BFS, we only have one, which is level order traversal. So we will see all four in one examples. Okay, so let's jump into the examples. Just taking it a random number, yeah. 20, 30, 50, 40, 60, 70, 80, right? So this, just take this as a R binary tree. Oh, is it a binary tree or not? Just compare it quickly. Yes, it is. We have 0, 1 or 2. Correct, guys? It's a binary tree. So now let's start from BFS first. Okay, let's start our traversing from the BFS. Let's start our traversing from the BFS. So on the BFS, what we were saying, on the BFS, if you want to traverse this tree, so what we were saying, we will be going with level order traversal, right? We will be going into level wise or level order traversal. So on the level wise, if we see, so first let us start from our root node of tree. This is the root node of our tree. Okay, so if you want to do the level order traversal, so this is the first level, right? Which is level 1. Correct. So in this level, you see only one element is there. So this would be the first element which will be printed out, 10. Correct. Then we will move into the next traversal, next level. We'll go into this level, which is level 2. Now the first element is 20. Then we have 30. Correct. And then we'll go into the next level, which was level is equal to 3. And we again start printing from the left side, 50, 40, 60, and 70. And now we'll go into the last level, level is equal to 4, where we have only one element, we will print 80 here. Okay, guys? Understood now the level wise traversal? Yeah. So it was about the level order traversal. Anyone has any confusion here? How to travel? How we are doing traversing in level order? Are we good with that? Okay. Now let's move into the next one, guys. Okay. Let's see what is that. How it is traversing. So, like pointer. Yes. That way we will check. We'll check, Hariharan. Like what is the strategy we will use to traverse in this way? Okay. We'll see that strategy. And I'm just giving you one hint. We are going to use Q to achieve this level order traversal. We are going to use Q there to do the level order traversals. Okay. Now let's talk about So now let's talk about the DFS. So in DFS we have 3 ways, which is pre-order. So I'm just writing. Okay, let's write pre-order traversal. Then we have in-order traversal, and then we have post-order traversal. And you know the logic as well. What is the logic for pre? Root, left, right. What is the logic for in order? So root would be in the middle, and then left and right. And what is the post order traversal? Root would be at the end, and left and right. Right, guys? That was the logic which we talk about. Left, right, root, right, or whatever is left, root, left, right. Correct? So now let's do the traversal. Start from the. So now we can see for the if you want to go for the pre. So now we can see if we start from our root label, from the root node of it. So this would be the first node. This is our root. We are going to be. So we can see first we have to print the root. So first 10 will be printed out here. Then it is saying go into the left side. So now we'll go into the left till here. This binary, this particular tree, the depth, we have to go into the depth now. So we can see on the, if we go into the left side, we will be reaching here. That would be our depth. right? So now we'll be printing 50 here, right? Let me check, right guys, we are doing correctly, right? So yes, that would be our left side, the top left here. Am I doing anything wrong? It looks like to me. 1 minute. Root, left, right, and then root, then would be left and right. Okay. I think we have to. I'm just thinking like we should come to 20 first. Then we should get 50. Yes, yes. I think yes. Let me check. By 1 minute, guys. Yes, DFS follows pre, post, and in. All of three. Let me just check 1 minute. One thing, guys. I think yes. I think we should go to 20. Let me check 1 minute. Now we can see this here in the pre-order. So in the pre-order, we can see here. Yeah, so 10 left, and then left also has left. Yes, 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 yes. Okay. I was just confused there. Yeah. Okay, so guys, yes, one we'll not go into the 50. Okay, so let me just repeat it again, guys. Okay, so see guys, again we will start from the root node and we are going to follow the same logic. I just missed it one. That's why I got confused here because I was just missing one thing. So you can see root, left, right. That's what we need to follow, right? Root, left, right. So root is 10 right now. So we'll print root, which is 10 right now. Then we'll go into the left side. Then we'll go into the left side. So once we come to go into the left side, we'll see this particular element. We'll see this particular element, right? So now we'll consider this as our tree, this as our subtree, this as our subtree. Again, we'll see that now we have to apply the same logic again for the left of this root node. For the left of this root node, we got again one subtree. So we have to apply the same logic again here. So root, left, and right. So root would be 20 there, and left would be 50 there, and right would be 40 there. Understood, guys? We are talking about, see, we started from the root node and we are trying to apply the same logic, root, left, and right. Let me write it correctly also. Some people might be confused with this. So this is root. Let me put the comma also. Left, root, right, left, right, and root. Okay. So first is the root. So that's what we have traversed when we started traversing from the root node of tree. So we got the root here. So we have printed it out, which is 10 here. Correct. Then we are going into the left side. We are going to the left side. So once we reach the left side, we have taken it as a subtree. We have taken it as a subtree, and we are going to apply the same logic there again. Root, left, and right. So in the root we got 20, in the left we got 50, and in the right we got 40. Understood, guys? First, let me know. Did you guys understood this part? Yeah, it is recursion. I was actually confused earlier, but now are we good with this? Everyone understood? Repeat. Okay. So Suraj, what we are trying to do here, we are trying to do DFS first, which is DFS, which is depth first search. We need to go into the depth, and then we have to start printing out our elements. Okay, so what we did in the DFS, we also have three ways: root, left, and right. Root, left, and right. So see, in the whole tree, this is our root, right? Root node of a tree. So first we printed out this one, which is 10 here. You can see the output is 10 here. Then we are going into the left side of this root. Left side of this root. In the left side of root, we got again one subtree. So we are going to apply the same logic there as well. Root, left, right. So you can see root is 20 here. So we put it 20 here. Then we have left, which is 50 here. We have put the 50 here. Then we have the 40. Then we have 40. Correct? Because they do not have any because they do not have any further subtrees. That's why we are not traversing there. That's why we are not traversing there. Because we have already told you how we will be stopping our traversing. We will be only stopping our traversing when left and right are null. When left and right are null. Okay. So now we have already traversed all the left part of this route. All the left part of this route we have already traversed. Now let's go for the right part of this route. Right. So now we'll go for this part. Let's take the blue one. Now we'll go for this one. This is our second subtree, whole. Correct? Now this is our second subtree. So what is the, again, same rule, root, left and right. So what is the root here? Which is 30. So I believe 30 will come here. Correct? Now we'll go for the left side of this root. Now we'll go for the left side of this root. Correct? So again, guys, internally, it will create again, I think this is the left, right? So this would be the tree. This would be the subtree. This would be a subtree. Correct, guys? For this root 30, this would be a subtree. We are going into the left side of it. So we can see again we got one subtree. So again, same logic, root, left and right. So because in root, it's 60 is there. Then in left, we have 80. Because we do not have anything further, so we are not going for any other tree. And in right, we do not have anything for 60. So we will not go there. Now we will come back to parent one, which was 30. So we have already traversed the left side, already traversed the root. Now we have to go for the right side. And then now we'll print at 70 there. So this would be the pre-order traversal for the same tree. You can see, guys, for the BFS, we have this data. For the for the pre-order traversal, we have this data. Now we will be looking for in order and post order as well. But before that, you guys tell me, did you guys understood the pre-order traversal or not? Anyone has any doubt on the pre-order traversal? When we see any tree is coming, we have to create a subtree and use the same logic there. Root, left and right. And that's what same we are going to do for in order as well. We're going to do the same for that one also. Post order as well. Anyone has any how to go right? Suraj is saying how to go right. So see, Suraj, we have to only go right when we have in the pre-order. We have to only go right when we have after 80, not 70. After 80, not 70. No, that's right, right? You can see this is the root, this is all the left element, then we have the right element for 30. You can see 30 is the root. We have already traversed all the left of it, which is 60, 80. Then we have 70. Correct. For every subtree, we have to check conditions according to which method we are following. Yes, Arad. For every subtree, we have to check the conditions. Totally right. That's the condition we have to follow. Same we are going for the in order as well. Suraj, my question, how to go right? Yeah, I didn't understand your question. How to go right means. So answer to that question is, Suraj, that you need to follow the rules. 30. Because Suraj, we have already traversed the root and we have already traversed all the right element, all the left element. You can see 10, 20, 50, 40. We have already traversed all the left side of tree. So according to rule, once we have traversed the root, once we have traversed the left, we have to go for right. So that's why we started with 30. Because we have already traversed the root. First we have traversed the root, then we have traversed whole left, then we are going to the right. Understood, Suraj? That's why we are going for the 30. He's asking how to go to 30 from 40. Oh, that implementation part, we'll talk about it. Why you guys are worrying about it? Implementation part, we'll talk about it. If you want to know the hint, we are going to use stack here. For all the DFS operations, we're going to use the stack. And for all the BFS operation, we are going to use the queue. We'll talk about it. That's how we will insert elements into stack that after 40, 30 will come only. That's what thinking we need to do there. Okay. Now let's talk about the in-order traversal, guys. Now let's talk about the in-order traversal. In meanwhile, let me clear it out if I can clear these lines quickly. Okay. Because again, we need to create the tree, right? Or we can have another example, right? Yeah, we can have another example. Let's take down the same example here. 10, 20, 30, 50, right? Then we have 40. Let me provide the circles also. 60, 70, and 80. By the way, anyone wants to try in-order traversal first? Let's go. Let's go. Let me go for the in-order. Then you guys can try for post-order. Okay, last one. Let me go for the in-order. Whoever has any doubt, then we will look into that. So guys, for in-order traversal, it's saying left, root, and right. So we'll start from our tree, which is the whole tree here, which is the whole tree like this. Correct? So we can't, in pre-order, we have printed out 10, but we can't print it out the root right now. This is our root, right? So we have to go to the left of it. We have to go to the left of it. And then we need to go for the right. Then we need to, first we have to go to left side and we have to print the left side element. Then we need to print the root. Then we need to print the right side. Okay. That's what we need to do. So we will not print 10 right now. Now we'll go into the left side. So once we go into the left side, you can see this is the left side, right? For the root, this is the left side. So we'll again consider this as a subtree. Correct? We'll again consider this as a subtree. This is a subtree. Correct? Now again same logic. Left, root, right. So again we'll go into the left side of it, which is 50, which does not have any further subtrees. So that would be our first element which will be printed out. 50 here. Correct? Then after left, we need to print root, which is 20. And after root, we need to print 40. After root, we need to print right. So that would be 40. Now you can see we have traversed whole of left of root. This is the root element. In this tree, we have already traversed all the elements in the left side. So now we will print our root, which is 10. Now we will go into the right side. And again, on right side, we'll consider this as another subtree. We'll consider it as another subtree. Again, same logic. This is our root right now we are talking about. We have to go into the left side. Once we will go into the left side, we'll get this as a subtree. Correct? We already did the same in the pre-order. Now in this tree, we have to again go for the left side first, which is 80. So first we will print 80, then root, which is 60. Right? We do not have anything on the right side. So now left we have already covered. Now look for this one, the parent one. 30 is the root now. So we'll print 30. And then we already left has printed, root has printed. Now we'll go for the right side, which is 70 as well. So now you guys can see all these three we have printed. Now let me come to the chat now. So Likit has given answer. So 50, 20, 40, 10, 80, 60, 30, 70. Correct, Likit. That's right. That's for in order. Voice getting stuck. Is it happening for everyone? Okay. So did you guys face any problem while traversing the in order? While traversing in order? No, so let's quickly do for post order. Let's quickly do for post order. Let me also try in meanwhile. Do not see into my screen. Just try for post order. With the same tree. I'm drawing it again here on this side. 10, 20, 30, 50, 40, 60, 70, and 80. You guys just try it quickly. I'm giving you 3 minutes. You guys can try it and put it into the chat, and then I will go for it. Then you guys can compare it. Do the post order traversal quickly, guys. Post order traversal for this tree. I think this much time is enough, right? Let's see. Hariharan is saying pre-order once. Okay. So Hariharan has given the answer for post order. Okay. Arad has given. What about others? Arad, you can correct it yours one. What about others? Please paste your answer. Okay, so a lot of people has given the answer. So now let me start traversing it and then we can compare your answers. Okay, so let's look into this. So we'll start from the post order traversal, right? So on the post order traversal, our condition is left, right, and then root. Left, right, and then root. So right now, this is our whole tree. And this is our root. Correct? This is our root. So we have to go to the left side. Okay. So once we go into the left side, this will become our tree. This will become our subtree. Right? Now, again, this will become 20 will become our root. So now again, same logic. Left, right, root. So we have to again go to the left side. 50. 50 will become our root. Because it does not have any left, does not have any right. So first we will print 50 here. Correct? Because 50 is the last root here. Then now we have printed it out. For this element, we have printed out the left of it. Then we will print the right of it, which would be 40. Then the root, 20. So now we have already compared all the left of it. Now we have to go into the right side of it. We cannot print 10 because our condition is left, right, then root. So now we have to again go back this side and consider this as a subtree. So again, 30 will become our root. Left, 60. 60 will become again subtree. Correct? So now left, which is 80. Then right, we do not have anything on the right. So we'll go for root now, which is 60. Correct? So 80, 60 is there. Now we have traversed all the left of it. Now I'll go for right, which is 70. And then go for 30. And then we have traversed the left and right. Now we'll go for root, which is 10. So that should be our answer, guys. So 50, 40, 20, 80, 60, 70, 30, 0. Yeah, I think you all guys have given correct answer. Who has not given the correct answer, please correct it. And you guys, if any doubt, let me know. It looks like Joseph's answer are wrong. It's starting from 80. Hariharan answers is correct. Arad answer is correct. Joseph's answer are just little bit wrong. It is starting from 80, it looks like. Now, are we good, guys? With the left, pre and post order? Oh, you started with 50. Oh, then it's fine. That is fine. Then you started with 50, then your answer is started with 50 above. Okay. Okay, Joseph has given more answer, it looks like. Okay. Vishal's, okay. Vishal's answer, let's see. 50, 40, 20. Yeah, Vishal, your answer is little bit also wrong. 30. 30 should not come after 50, 40, 20. 80 should come after that. Vishal, did you understood why? Or you are I know and corrected it. Okay, corrected it. Okay. Yeah, he has corrected it down. Okay. Okay, guys. So that's what about the traversing part. Correct. So you want to try with one more example? Let's see. Yeah, I think let's take one more example which is given in the slides, and then we can look into the coding part quickly. Let's take this one, a smaller one, which is 10, 20, 30, 50. Let me just put it here. 10. Is this the same example we are doing it? 20, 30, 50, 40. Yeah, it's little bit different, right? 40, 70, and 80. Right? So first give me BFS, guys. This should be easy. Give me BFS quickly. Give me BFS for this, guys. BFS should be easy. Yeah, 10, 20, 30, 50, 40, 70, 80. Correct. So this would be our BFS. 10, 20, 30, 50, 40, 70, 80. Correct? Yes. So now, guys, quickly give me in order traversal. In order traversal. Do not do any mistake, guys. Think and do. Do not do any mistake. Think and do. Think and do. You know about the rules of in order. I'm just reminding you. It's a left, root, and right. For in order, the rule is left, root, and right. Do it quickly, guys. Just giving you some more seconds. No one has tried. What happened, guys? Okay, Arad has given answer. What about the others? Left, root, right. Try that. Only Arad has given answer. What happened with others? Nishant has given now. Okay. What about others? It's like a game, right? You have to just traverse left, root, right. Likit has given answers. Joseph has given answer now. 4 and 5 people has given answer. What happened with Vishal, Hariharan, Parag? I think I have not seen their answer. Suraj has given answer. Hariharan has now given as. Okay, do not copy paste, guys. Okay, Parag has given it. Okay, I think yes, enough people has given it. Let's see that. So left. So in this tree, we'll come to this left. This is our first left. So 50. Root of it 20. There is no right on 20. So we'll go back to the root part. So we have already traversed everything in the root or everything in the left. We'll print out the 10, which is our root. Now we'll talk about this subtree. In this subtree, this is our root. We'll go into the left side, which is 40. Correct? Then we'll go into the root, which is 30. Right? Now we are in this right side. Right side also have one subtree, which is 70 and 80. So the left is 80 here, and then root is 70. So I think this should be our answer. Let's compare it quickly. 50, 20, 10, 40, 30, 80, 70. Yes. Yes, I think Suraj Hariharan has little bit different answer. What about others? Suraj has given 70, 80. Okay. Hariharan is correct, right? 80, 70. Yeah, Hariharan is correct. Yeah, Suraj's answer is wrong. 70, 80 is put it in the last. And Sharad, Likit, Joseph, Parag, Nishant answer is also wrong. Arad answer is correct. Joseph is given two answers. Okay, so second one is correct. Hariharan's answer is also wrong. Vishal has given, I think, second time or what? Are you guys not able to see me? Okay. Suraj, you just need to refresh your browser. So I hope you guys have understood this one. Let's now go for post order. Quickly, guys. Go for post order this time. And I'm expecting nobody will do any wrong assumptions here. Go for post order, guys, for the same tree. And for the post order, the formula is left, right, and root. Okay, Arad has done it. Nice. What about others? Okay, so let me try it post order quickly. So left would be 50. There is no right, so that's fine. Go for root, which is 20. Okay, right? We have already covered the left. Now let's look for the right side. Right side, we again have one subtree. So we'll go for this 30 as our root. We'll go into the 40. This is our left. Then we'll go into the right side. We again got one subtree. We'll look for 80 left. There is no right. We'll go for 70. Now left, right has been covered. Go for the root, 30 and 10. I hope everyone has been same. Yes, all four looks correct. It means you guys have understood it. Very nice. All four looks correct. Anyone trying to paste it or write it your answer? Otherwise, if everyone's answer is same, then no need to do that. Okay. Let's now quickly do the last one also. Why I left it? Pre-order as well. Where we have root, left, and right. Do the pre-order also. Quickly, guys. Root, left, and right. Root, left, and right. You guys have given the answer or what? No, nobody has given the answer. Please try it, guys. Do not be in a hurry. Try it, no problem. We'll wait for 1 minute. Okay, so now I think 4 and 5 people has given answers. So let's quickly look into that. So root, which is 10. Then we have to go for the left and right. So if we go for the left side, this is our, again, a subtree. So root left, root is 20. Then we have left, which is 50. We do not have any right. So we have covered the left side of it. Now we'll go for the root side, right side. In right side, we have this subtree. Again, root, left and right. Root is 30 and left is 40. And on the right side, again, subtree. Root is 70 and left is 80. That should be our answer. Let's compare it. 10, 20, 50, 30, 40, 70, 80. Okay. Hariharan is correct. Suraj, yes, correct. Arad, the answer is also correct. Yes. So everyone now comfortable with all these 4 traversals? Everyone is comfortable now? Anyone and any doubt? Let me know, guys, quickly. Yes. Okay. So now, guys, if we talk about the code now, if we talk about the coding part also, it's very easy. If we go with these pre and post and in order with the recursion approach, guys, it's very easy. Let me show you. If I just want to create for pre-order, for the pre-order, so see, my function would be function pre-order and here I will pass my root node of a tree or a node, right? This would be my pre. Right now, guys, I'm not talking about the what happened with my screen. Are you guys not able to see it? It's fine. Okay. So guys, I'm right now talking about the recursive function, not about the. See, there are two ways to implement these traversing. One is through the recursion way. Second one is the iteration way, right? One is the recursion way. Second one is the iteration. When I'm talking about the iteration way, means using while or for loop. While using when we use the while and for loop. And there is recursion way. Recursion where we call the same function again and again. Correct? So that first we are going to look from the recursion way. Okay, guys. So let's look into this. If we talk about the pre-order, so it's easy, right? First, simply console.log root.value, right? Like each node has three keys: val, left, and right. Correct? So if I am at this node, so I will first print 10. So that's what root.value is 10. Correct? And then if I have any left, go for the left side. So my condition would be if root.left, then call the pre-order function with root.left, because this is again a subtree. Correct? Root.left is a subtree. So then again first call the pre-order with root.left. So first we'll call the root.left here. So this whole tree will be passed there. This whole tree will be passed. Again, in the pre-order, we'll get the same tree again. Again, we'll print the root.value, which is 20. Again, we'll print the 20 here. Correct, guys? We started with root node. This one, we printed the first value, root.value. Correct? Which printed the 10. Then what I'm checking? Because I have to go for the left side now, because root is already printed out. I have to go for the left side. So what I did, if my root or if my root node has left, first traverse the left side of it. First traverse the left side of it. So first I will pass this whole node or this whole subtree to my pre-order function again. And then I'm again, once the second time this subtree is coming, so root is 20 here. So I will be printing root.value as a 20. So that's why you can see 20 has been printed out. So first 10, then 20. Again, I'm checking if my root has left. Yes, I have. My root has again left, and which is this one, 50. I'm again passing it. You can see root.let. I'm again passing it, and again I'm doing the root.value. So first I will get the 50 there because this root is 50. Now it does not have any left. Now check for right as well. If root.right, it's very easy code, guys. And then if somebody has right, then pass the right side of it and print that value. Only these are the 6 lines, guys. How many lines are there? 1, 2, 3, 4, 5, 6. Yeah, 6 or 7 lines, and you will do the pre-order traversal. Now, because it does not have root and right, it will be written from here. So now it means we have already traversed whole of this part. Now we'll go for the right side. Correct? For 10, first we traverse the left side. Now we are going for the right side, and same logic will work there. Again, new root will come. We'll get the root.value and root.right left. And at the end, if you want to return it, you can write at the end return null or return simply return without any value. Correct? Correct, guys? That's easy. If we want to do with the recursion, it's easy. We just need to first print out the value in the pre-order. And if any node has left side, first traverse the whole left side. If any node has right side, then traverse the whole right side. Are we good with that, guys? Same code, guys, very same code. Same code is going to work for in order as well. Same code is going to work for in order as well. It just, you need to change the positions now. You just need to change the positions now. Correct? In order, in order, you remember root, we need to print root in middle. And first we need to check the left, then right. Same code will be in this position. If first we'll check the if root dot left. So first go for the left side. In order, root dot left. And then do the console.log. Once we have reached to the all the left, then we will be going for printing out the root dot value. And then if root dot right, see the same logic which we remember here, same will apply here also. If root dot right, again call the in order root dot right. Correct? This is the code for in order, guys. Pre-order and in order. And same code for post order also, guys. It just, you need to change the pattern. In the post order, left and right, and then we have to go for root. So in the post order, first these two conditions will run. And then we will do the console.log. See, with these 6 lines, we have covered all three traversing here with recursion approach. Yes, for post order, console will come at last. For post order, console will come at last. Understood, sir, but where is the code for in order and post order here? You guys are not able to see my screen? I didn't understand this question. This is the code for pre-order, Joseph. And this is the code for in order, similar way. And I have not write the code for post order. How do we sort the tree? We'll look into that, Ankit. Today we are not going to discuss about the sorting part. First, we have to understand how to insert element into the tree. Then we will look into the sorting part. Okay. Joseph, understood now? Like I did, by the way, I also have not understand your question when you said where is the code for in order and so this is the function name, right? Pre-order. So just recursively calling it. Yeah, no problem. What will be self work here? Self work here. Can you just elaborate your question? What do you mean by that? Okay, in meanwhile, let me show you this code also, guys. I have it in 1 minute. In the repo. I think you guys can see that in master only. In master branch only. Yeah, you can see I have implemented first tree node. Because insertion we will be looking later. That's why I'm not showing you the insertion part right now. But yes, we can see that in order with recursion. So I've taken my current node and you can see I'm just traversing it. First I'm traversing node dot left, then I'm traversing node dot value, like consoling it, and then I'm traversing the right part. Correct, guys? Are we good, guys, here with the recursion approach? If I have pre-order recursion, no, we do not have. But yeah, we can implement the pre-order as well. You can see I have taken my first node, which is the root node. Then I'm passing that node in the traverse function. And inside traverse function, I'm just calling it again and again. You can see if any of my node has left, first traverse all the node, all the left side. Once you have traversed all the left side, then you will go into the next line. You know how the recursion works. You know that, right? How the recursion work. Once we will complete all of the previous lines, then it will go into the next line only. So that's why till this function will be completed, we will not go into anywhere else. continuously, and after that, when we reach to the last left node, we will be printing out that node, and if that node also have any right side, we will be traversing that right side as well. Okay. In recursion, we have some conditions like base case recursion, call and self work. So what will be that self work? Okay. So see, Nishant, you are stopping it here. You mean like where your recursion will stop, right? That's the base condition you're talking about. So your condition, yes, base case, yeah. So your what we are doing here right now, our base condition is this one. If left dot this one, if node dot left, if node dot right. That's what I told you in the starting only when we're talking about the where we will stop it in our recursion method. Wherever we do not have any node left and right, we will be stopping it there. That's our base condition, Nishant. Because we do not have any in that node, we will stop it. He's asking self work. And if you're talking about the calculation part, like if we are doing any calculation here or not, so we are not doing any calculation here. We are just simply printing it out. Yeah, we are just simply printing out the nodes. Traversing means that only. We have to print it out. Okay, guys? Are we good with the coding part, guys, for all those three scenarios? Let me show you one iteration with the iteration approach also. Yeah, self work is printing here. Yes, Likit. Printing is self work here, correct. Okay, guys. So now let's look into the for one of the I think way. Just look for the iteration approach also. And I have already told you for all the DFS approach, stack would be very helpful. So I will be showing you one of them, and I want you guys to try it for other traversals also. Okay. For I think in the code I have for two. In order also I have. If you want to see my code, I have in order and pre-order. Both traversal I had with the stack. What I want you guys to implement, I will just show you first of them with the stack with the pre-order, and then I want you guys to implement for others. Okay. Okay, so now let's first while we use, okay, so there is 3 ways to manipulate the tree or traverse the tree. 4 ways, Ankit. You are forgetting about the BFS part. Correct? There is a 4 way to traverse a binary tree. Now let's quickly see, guys, the pre-order traversal with iteration approach. This was the recursion approach. Now let's quickly look the pre-order traversal with let's quickly draw that 10, 20. I just want to give you one idea so you guys can try it later to implement other 50, 40, 70 and 80. So let's take a stack here. Okay. So what we will do, guys, first in this stack, we will be first pushing this element 10. Correct? So first push this element 10 here, because you know that in a stack on the top element on the because you see in the pre-order what is the logic here? Root, left and right. I think this one is very easy. I think we do not need to print 10 also. We do not need to insert 10 also. You can see what we'll do. We'll take one stack here. Stack here as an in JavaScript we take it as an array, correct? And then we need to put a condition there, like we can put a while condition there, while yeah, let's 1 minute. So let's take in this stack, let's take the root element, no problem. Let's take the root element 10. Okay, because it will help in our while condition. So we can take a while condition here, while stack dot length is greater than 0. Correct? It will provide us to enter into the while loop because we have printed out this element. Correct? Now pop it, because in the stack we have only two operations, push and pop. Correct? So we have pushed this 10. Now first pop it. So now we are popping it. So I'm just writing as a node. Correct? So let node is equal to stack.pop. Correct? Now we have popped it out. So now our stack is empty. Correct, guys? And we have this data here. So first console it. Console.log node.value. So we got the 10. Right? Now we are checking same thing. If node.left, push in stack, stack.push, node.left. And same for if node.right, or wait guys, there is some mistake. Node.right. I think this will be opposite. Node.right will be first push, then node.left. 1 minute, let me check. If node.left and node.right, yes. So if we will push the node.left, 20 will be pushed, right? And if then we will push node.right, which will be 30 would be pushed. Okay. Which is wrong, right? Which is wrong, correct? Now we'll pop it, 30 will be popped first, which is wrong. So guys, just little twist. We need to first do the right here. Just for the stack, because of the stack feature, we need to remove this line from here. I will show you this will work or not. And then we need to first push right and then push left in a stack. Let's see this strategy will work here or not. Stack.push, node.left. Let's see this strategy will work here or not. Guys, easy, right? Let's see first this strategy is working or not. So first we'll push node.right. We'll pushing 30 here. Okay. Then we are pushing node.left, which is 20 here. Correct? Now our loop has ended. Now we are coming back to again to this while loop. While stack.length is 0. So now in this stack, 30 is there and then 20 is there. Correct? Now we are again popping out. So 20 will be popped out. So 20 will come here. Node.value, 20 will be printed out. So 20 will be here. Again, node.right. No, we do not have anything on the node.right. So we are good. Node.left. Yes, we have 50 there. So we'll be pushing out. We will be pushing out 50 there. Correct. This will work, guys. 50 will be there. Now again, our while loop will ending. We are again checking stack.length. From here, 20 also remove. Put the 50 here. Again, we will do the popping here. Go for 50. Correct? Then we will be printing out 50 here. Because 50 does not have any left and right. That's fine. 50 does not have any left and right. So now in stack, we only have a 30 there. We only have 30 there. So now again, first we will print the 30 there. So 30 will be printed out. Then right, we'll push the 70 there. Then we'll push the 40 there. We do not have anything for 40. So we will be printing out 40. Correct? Then we will go for 70. 70 will be posted out. And 70 has 80. So 80 will be printed out. 80 and then 30. Is it the same? We have done it. 10, 20, 50, 30, 40, 70, 80. 40, 70, 80. Oh, 30 is not needed. 30 we have already taken it out. Guys, this is the code in Traversal for the pre-order. Without recursion with while loop. Let me know in the chat. I'm sure you guys might be confusion there. So there's three way. Okay, my bad. While left is not equal to null, push root.left.data, and after all pop and print same for right. While left is not equal to null. Okay. push root dot left dot data, okay, and after all pop and print same for right. So Likhit is saying, well, root dot left is not equal to null, so push that root dot left dot data, okay, and after all pop and print same for right. Likhit, just try to implement it and let me know in the LinkedIn. I will check this code. Yeah. Okay, guys. So that's what about the pre-order. Anyone has any question on this pre-order traversal with the iteration approach? You can post it in the group. Okay. You can put it in the group. I will check there. Guys, anyone has any questions? Let me see the pre-order iterations. Yeah, you can see the same code which is written here. But yes, I'm telling you, try now, guys. Try that. Yes, Nikit, I have seen that. But because right now I think there is very little, because I think PayPal has also stopped right now the internship opportunities. So right now I'm just waiting for if they provide any information on that. I will just refer your like yours and Joseph and whoever has share the resume. I will just apply for that. Yeah. Joseph, which part? Which part you have not got? Yeah, I'm talking in iterative which part? And in the stack traversing or the whole part you want me to repeat it? Okay, sure. Arad has also not understood. So let me repeat it again. Okay. So this is our stack, guys. I have taken it as an empty stack. Okay. And then what I did in this empty stack, I just pushed the top element, which was 10. Correct? So now in this stack, 10 is here. In the pre-order traversals, you know that first we need to print the root, then we need to print the left, then we need to print the right. Correct? So in stack, you can see what we did. First we printed out, first we popped it out, this element from the stack. You can see. So we got our node 10. This is our node 10. Then we first printed out this 10. Printed out the value for that node, which was node.value. So now we got the 10 here. Then we are looking for if it has any right, then first push that right, because we have already popped out 10. So now first we'll pushing out the right here. Then we'll be pushing out the left there. Now you guys can ask why we are pushing right first. The reason for how the stack work, because in the stack we can only pop the element which are on the top, So that's why we need to smartly think how to push element in the stack. So that's why we first pushed right side, then we push the left side. So, but in the stack, you can see now the left side is on the top. And now when the next time you will be popping out, you will be popping out the left side element, not the right side element. That's why we smartly change this logic. If node dot right, if there is any node dot right exist, push that element first, then go for the next node. Understood, guys? That's why we did it. We can pop on top. Should we do the opposite of what we do usually? No, do not remember like that. Anna, do not remember like that. While we are doing the traversing, that's fine. While you're doing the iteration approach, while you're doing the recursion approach, then it's fine. You just remember that logic, right? But when you are writing the iterative code, you need to think about the stack. See, when you will working with the in order and post order, you will be like this same logic will not work there. In order and post order, the same logic is not going to work there. You have to think about how to insert element in the stack properly, so you can get, because see, in the stack you can only take it the element which is on the top. So you need to somehow smartly insert there in the element in the stack, so you can just every time according to your rules, you can get that top element and put it out. Okay, guys. So just I told you about this pre-order. I want you guys to think little bit about. Do not just look into the internet anywhere. Please little bit think about in order and post order. It will definitely clear your logics as well with the iterative approach. Okay, guys. So that's all from today's class. I think we'll connect back on next class and we'll talk more about them. We'll look into the post and pre-order iterative approach as well and BFS as well. And then I think we have some assignment questions. So we'll look into those assignment question as well. And then we will start our next topic, which is BST, binary search tree. But yes, before that, please practice these problems, which I told you, which is in order and post order traversal, or if you want to try for the BFS also, try that. You just need to use the queue instead of a stack. Okay. So try all these three problems, guys, and we will connect back on Wednesday. Okay, guys. Yeah. Good night, everyone. We'll talk in next lecture. Yeah. Bye-bye.